Hello everybody. We're still talking about the absorption in Aspen Plus, and in the previous video we saw that we were able to remove or purify air from the ammonia by absorbing the ammonia using fresh water. And the absorption was successful, and we produced air that's almost 98% pure, and we have already achieved the goal of recovering 95% of the ammonia from the air. And now the goal of this video is to recover this stream. It contains 90% water and the rest is ammonia and air. And we want to recover the water so that we can reuse it here, as we mentioned before in the video of the discussion of the absorption and stripping, to make the process more economic and to reduce the amount of fresh solvent that we are using. So what we're going to do is add a new column here. Which one of you can use one of these? I'm going to use this because or this, whatever one you want, because it contains a condenser and reboiler, which is what I need in my case. So what I'm gonna do here is to call this as stripper, and connect this as the feed to the column, and add a bottom stream and the top stream. Keep in mind that there are two, you can pick one of these two, which is either a liquid distillate or a vapor distillate. In our case, I'm not producing liquid because the product is vapor, and all the condensed stream is recycled back to or as a reflux stream to the column. So it should be connected here. And keep in mind that this is critical, that you know that the input that you put is consistent with the input, or the connection that you connect here is consistent with the input that you put inside the column. So this is something that we will visit in a few minutes. So I'm gonna call this the product ammonia, and I'm gonna call it the regenerated solvent. And now let's see what kind of inputs that we have. So the first, I'm gonna go for equilibrium stages calculations, and I know from before that 7 stages are enough. You can do this by using shortcut calculations or by doing manual calculations depending on what you want, but 7 is okay. Now I know that it's a partial condenser with a vapor distillate. But in case you use total condenser, this is not going to be consistent with the connected stream. So it's going to give you this consistency error that the phase equal vapor or total vapor, which is the stream that I connected in the flow sheet, is not allowed for distillate stream when condenser is total. So I have total condenser, it's not consistent. So I have to use partial condenser with vapor distillate. I'm gonna use kettle boiler, vapor liquid streams, and I'm gonna go for petroleum and white boiling because of the same reason I mentioned before, or I used before in the absorption column. Now let's go for the operating specifications, and again the specifications reflect your understanding of the column or the function of the column and the goal that you want to achieve from it. So I know that I want to recover 986 if I can. This is the maximum amount I can recover, but this is the amount of water that I can recover in the I want to recover in the bottom product. So it's more realistic to go for the bottom rate, and I would go for 982, which is little less than 186 because it's not realistic to put or recover all the amount of water that you have in the rich solvent stream. If you put 986, it's going to give you a lot of impurities with the water. So it's not going to give you 986 pure water, but it's going to be 986 containing a lot of ammonia and air. So it's not the logical to put the exact amount. Now for the second thing, you can use reflux ratio, but reflux ratio is not the best option here. Reflux ratio is the amount of the vapor that's coming out of the condenser divided by the amount of the liquid that is recycled back to the column. And the amount of vapor is very little compared to the amount of the liquid recycled to the column, so it's not you don't have a good estimate of this number, and we don't know exactly what is the amount of water that's recycled to the column from the condenser. So the number could be 15, could be 20, could be 20 something. So I don't have a good estimate of this number or a narrow range for this number. So it's better to go for the boil-up ratio, and this is more logical because again, let's go back to the flow sheet. the boil-up ratio is this amount divided by the bottom product. It's exactly like this amount divided by this, which is the reflux ratio. So this is the boil-up ratio. So it tells the, or it kind of indicates how much of the bottom product is used back in the column. And we mentioned before that this is the parameter that then I can use to control the column or improve the stripping in the column. So I'm going to go for 0.5 for now. And this is something that we can change in the future in case it's not giving good results. And for the streams, the rich solvent is going to go above stage number 1. And for the pressure, I'm going to use low pressure compared to the absorber. We used 6 atmospheres in the absorber. Now I'm using 2 atmospheres, and the pressure drop is going to be 0.5. So it's going to be 2 and from 2 to 2.5 bars in the column. So this is everything for now. I'm going to run the simulation now and see what kind of output I'm going to get out of it. So luckily it's giving the results, no errors. So now let's take a look at the results of the stripping column. The first thing that you can check, which gives you a good indication of the performance of the column, is the temperature of the condenser and the temperature of the reboiler. So the condenser is 54 and the reboiler is 127. Keep in mind that this reboiler pressure is 2.5 atmosphere. And the temperature here should be the temperature or the boiling point of water, because I should be very high percentage of water in this stream, so it should be almost like pure water. So the temperature here should be the boiling point of water at 2.5 atmosphere, which is logical. I don't know exactly the number, but it seems like a logical number because it's 100 at 1 atmosphere, so it's higher at higher pressures. The same here, this temperature should reflect the condensation, or should be the temperature at which water is condensed and ammonia is not. So this sounds like a good or a logical temperature. And now for the split fraction, we see that all the air is coming at from the top product. 99.3% of the ammonia is recovered in the top product, which is great, and 99.5% of the water is produced as a bottom product. So this sounds like great. From the profiles, we can take a look at the composition profile, just to make sure that all the stages are adding something to the column. So it seems that the compositions are changing as we proceed from top to the down. So it seems that all the stages are doing something new or adding something to the column. Finally, let's take a look at the stream results. Here we see that the mole flows, I have 981.3, and the rest is the impurities. And this is what I mentioned, even the 982 are not pure water. There is still some percentage of ammonia. It's very small percentage. It should be, if we take a look at the mole fractions, it's 99.93, and this is 0.06%, which is very negligible. I have almost 90% ammonia in the air or in the top stream, and this looks great. I feel that, or I see from the numbers that the operating conditions are very good. Still, you can do more work with the stripping column to learn more about the effect of the parameters on the column. So you can do sensitivity analysis on the stripping or the boil-up ratio to see how this affects the mole fraction of ammonia in this stream. Or the amount of ammonia we're producing here. You can change the pressure of the stages, as we did in the absorber before. And this will give you a good indication of the performance of the column. And this is one thing that helps you have a good feeling of the numbers and the effect of the parameters on the performance of the column. So for instance, if I change the boil-up ratio, if I decrease the boil-up ratio, I should expect that this will reduce the efficiency of the column. So I should see see more ammonia coming here if I reduce the boil-up ratio, because the vapor that is meeting the liquid is less. So it's not good for the removal of ammonia from the air. Again, for the pressure, if you increase the pressure, this should have a negative impact on the performance of the column, because the high pressure reduces the a driving force, and it has like bad effect on the stripping, as we mentioned before as well. So I'm not gonna do this because we have done that before, and I'm not gonna be repeating the same steps. And this should be a good exercise for you if you wanna do it and try it yourself. So this is all for this video. The next video is gonna be about the recycling of this stream. We have already done the recycle of the solvent in the extractive distillation before. But I believe that the recycling is one of the trickiest things in the Aspen Plus, so I feel that it's better to do one more practice on it, so that we make sure that we do all steps well and we don't mess up with anything. So this is going to be the topic of the next video, inshallah. So I'll see you then. Goodbye.